Most people think sailboats work by having the wind push them forward, but that logic breaks down when a boat sails against the wind and moves faster than the wind itself. Well, not straight against the wind, but within 45 degrees of it. Downwind, yes. The sail catches wind like a bucket. Wind pushes the fabric. Boat moves forward. But sailing upwind, that model is completely wrong. The sail is working like an airplane wing. Hold a piece of paper by one edge and blow across the top of it. The paper lifts, not because you pushed it, but because airflow over the curved surface accelerates, drops pressure, and the higher pressure underneath pushes up. Bernoulli's principle. Dot, dot. A sail does the same thing standing vertically. The curved leeward face. Leeward means the downwind side. Accelerates airflow. The pressure difference creates a lift force, not upward, but forward and sideways simultaneously. Strictly, the accurate model is circulation theory. Lift arises from the net circulation of airflow around the foil, described by the Kutta-Joukowsky theorem. Bernoulli captures the pressure difference correctly, but not the mechanism. The formula is the same either way. Every part of the boat has a job. The bow is the front, the pointed end that cuts through the water. The stern is the back. The hull is the body of the boat. The gunwale is the top edge of the hull on each side. The rail you hook your feet under when hiking. The mast is the vertical pole everything else hangs from. The boom is the horizontal pole at its base. The mainsail's foot runs along it. If you hear jibe ho and do not duck, the boom will introduce itself to your head. The mainsail is the primary sail, attached to the mast and running along the boom. Batten pockets run horizontally across its trailing edge, stiff rods that hold the sail's designed curve, rigid under load. The jib is the forward sail. It attaches to the forestay, the wire running from the bow up to the masthead, and hangs in the triangle of space forward of the mast. Its clew trails back into the cockpit where the jib sheets attach, one on each side. Only one sheet is active at a time, the leeward one, trimmed to control the sail's angle. The windward sheet stays slack. On a tack, you release one and grind onto the other. Together, the mainsail and jib create a slot, a narrowing gap between them that accelerates airflow and amplifies lift beyond what either sail generates alone. The jib's trailing edge acts like a venturi, a narrowing channel that accelerates flow through it, pushing faster air onto the mainsail's leeward face and increasing its effective angle of attack. How steep-lie the sail faces into the airflow without crossing into stall. The shrouds are the wires running from each side of the hull up to the mast. Lateral support. The forestay is forward. The backstay runs from the masthead to the stern. The tiller is the lever in the cockpit connected to the rudder. Push tiller right, boat turns left. The rudder deflects water to the left, pushing the stern right and pivoting the bow left. The rudder is the vertical fin hanging at the stern. It steers. The centerboard or dagger board is the retractable fin below the hull. On small boats, it slides up and down. On larger boats, it is replaced by a fixed keel, a heavy ballasted fin permanently attached. Both do the same job, resist lateral slip, and keep the boat from being pushed sideways by that lift force. Halyards are the ropes that hoist and lower sails. Sheets are the ropes that control the sail's angle, the main sheet for the mainsail, the jib sheet for the jib. That sideways lift force tries to tip the boat over. Windward is the upwind side of the boat, where the wind comes from. The crew hangs out over the windward gunwale as a counterweight. Feet hooked under the tow rail, knees bent, body over the water. Keeping the boat flat keeps the sail in its optimal shape and keeps the centerboard deep where it resists sideways slip. Let the boat heel too far and you lose both. On a well-sailed boat, the windward rail is always occupied. Sitting inside when you could be hiking is giving away riding moment, and riding moment is free speed. The lift force has a formula. F lift equals 1/2 times rho, air density, times v squared, airflow velocity over the sail, times A, the sail area, times CL, the lift coefficient capturing the sail's shape and angle of attack. Here's the key. If the wind doubles from 10 to 20 knots, what happens to the lift force? It quadruples. not doubles. Quadruplus ductus quadruplus. That is why wind speed matters more than sail size. That lift force points perpendicular to the airflow, mostly sideways. The forward component is F drive equals F lift times cosine of the angle between the lift vector and the boat's heading. The keel resists the sideways remainder. What is left is forward drive. In practice, the boat does not track exactly where it points. The sideways force causes lateral drift called leeway, typically 3 to 7 degrees upwind. The actual VMG calculation uses your course over the ground, not your compass heading. When you are moving through the air, the wind you feel is not the true wind. It is the vector sum of true wind and your own motion through it. Call the true wind vector VW at angle theta from your heading. Call your boat speed VB pointing directly forward. The apparent wind, what your sails actually feel, is PA equals the square root of VW cosine theta plus VB squared plus W sine theta squared. If true wind is 10 knots from 45 degrees off the bow, and you are doing 7 knots, the apparent wind is not 10 knots. It is not 7 knots. It is something faster, arriving from further forward. The apparent wind is roughly 16 knots, arriving from about 27 degrees off the bow. Faster tutting from further forward. Sailing upwind, you feel more wind than actually exists, and it hits from a tighter angle than the true wind. Your sails must be set for that tighter angle, not the true wind direction. You cannot point your boat directly at an upwind mark and sail there. The sail stalls. The boat stops. You tack zigzag at an angle to the wind, and optimize for velocity made good. VMG equals boat speed times cosine of the theta, where theta is your angle to the wind. At 0 degrees, straight into the wind, VMG is 0. At 90 degrees, beam reach. You are moving fast, but making 0 upwind progress. VMG is also 0. The maximum is somewhere in between, typically 40 to 45 degrees off the true wind for most boats. On a dead downwind run, sailing straight away maximizes VMG, only if that is also your fastest point of sail. For many modern racing boats, it is not. They jibe downwind at angles because the boat speed gained from a better apparent wind angle outweighs the extra distance sailed. On a beam reach, wind at 90 degrees, a well-sailed racing boat can exceed the wind speed by 1.3 to 1.5 times. Apparent wind physics compounds as the boat accelerates. The faster you go, the more the apparent wind shifts forward. The better the sail works, the faster you go. A self-reinforcing loop kept only by drag. The beam reach is the fastest point of sail in raw speed, but fastest in a straight line is not fastest to your destination. VMG is what determines routing, not top speed. Is there a formula for the exact optimal angle? Yes. Sailboat designers build a polar diagram, a performance curve mapping boat speed against every possible wind angle at every possible wind speed. The optimal VMG angle is found by drawing a tangent line from the origin to that polar curve. The tangent point is your target. This is a constrained optimization problem, similar to gradient descent in machine learning. The polar is smooth and on a model, so the global maximum is reachable. The polar is smooth. OG equals VB theta times cosine theta dot works. If you wanted the exact optimal angle analytically, how would you set up that optimization? Formally, you are maximizing VMG QB of theta times cosine. Setting the derivative to 0 gives VB prime over VB equals tangent of theta. The slope of the polar relative to the radius equals the tangent of the angle. That is exactly the geometric condition the tangent line satisfies. In practice, sailors use pre-computed polar tables. Given wind speed and angle, here is your target boat speed. The instruments compare actual speed to target in real time. 5 main regions of the compass relative to the wind. The no-go zone, roughly 40 degrees on either side of dead upwind. No lift is possible here. The boat stalls. Inside that angle, the sail's angle of attack exceeds its stall point. Airflow separates from the leeward face and lift collapses. The same physics as an airplane wing stalling. Close hold, just outside the no-go zone. Maximum upwind VM title. Sails trim tight through hiking. Beam reach. Wind directly abeam at 90 degrees. Fastest raw speed. Sails eased to roughly 45 degrees. Broad reach. Wind from behind at an angle. Fast and comfortable. Sails eased further. Dead run. Wind directly behind. Slowest for most boats. Sail early out. Spinnaker deployed on downwind legs to massively expand sail area. A spinnaker can be 2 to 3 times the area of the mainsail. The spinnaker is a symmetric or asymmetric balloon sail that generates drive differently from the mainsail. Downwind, the boat is no longer flying a wing. It is partly catching wind like a parachute and partly generating lift from the curved surface. The physics is a mix of both. Your job flying the spinnaker is to keep it on the edge, full and drawing without collapse. The sail wants to either collapse inward at the luff, the leading edge, or blow out and go dead if you overtrim. The correct trim is just barely before collapse. The tell, watch the luff of the spinnaker. When it starts to curl inward, you are on the edge. Ease the sheet out until it just begins to fold. Then trim back 1 inch. That inch is where maximum projected area lies. Hold it there. Every few seconds, the boat's speed changes, the apparent wind shifts slightly, and you ease or trim again. It never stops. Why does boat speed change the trim? Apparent wind again. When the boat accelerates, say you surf down a wave, the apparent wind moves forward. The sail needs to be trimmed tighter, or it will collapse. When the boat slows, apparent wind swings aft, and you ease, or the sail will stall. You are not trimming to a fixed angle. You are trimming to a moving target. The catastrophic failure mode is a wrap. The spinnaker twists around the forestay and locks up. Wrapped spinnakers end races. They happen when the sail collapses fully and the boat's momentum drives the fabric into the stay. The prevention, never let it fully collapse. The moment you see the luff fold more than the leading edge, sheet in. Anticipate, do not react. In practice, how do you know if the sail is trimmed correctly? Ease it out, let it out, until the luff, the leading edge, begins to flutter. Trim it back in, pull it in, just until the flutter stops. That is the edge of maximum lift. Racing sailors do this continuously. You can do it too. Attack is how you turn through the wind going upwind. The bow swings through the no-go zone, and the boat emerges on the other tack. The sequence. Helm calls ready about, crew confirms ready, helm says helm's a lee and turns into the wind. Oil. The jib sheet on the old side releases. As the bow crosses through the wind, crew grind the jib onto the new side. Everyone moves weight to the new windward rail. 5 to 8 seconds on a well-drilled racing dinghy, closer to 20 on a larger cruiser. A jibe is the downwind equivalent. The stern passes through the wind instead of the bow. The difference is the boom. In a tack, it crosses slowly as the boat turns. In a jibe, it swings across hard and fast with the full force of the wind behind it. An uncontrolled jibe in heavy air can break the mast. Controlled jib, ready to jibe, jibe ho, center the main before the turn, controlled sweep across, sheet in on the new side. Fast and clean, 5 boat lengths gained. Slow or chaotic, 5 boat lengths lost. You can gain distance not by having a faster boat, but by processing information better and faster than your competition. The water surface tells you where the wind is. Dark ripple patches, pressure. Glassy flat areas, no wind. Root around them. Clouds tell you what is coming. Cumulus building over warm land on a summer afternoon means thermal wind, riding offshore within the hour. Other boats tell you what is happening right now. If the fleet on the left side of the course suddenly accelerates, wind filled in over there, in real time. The skill difference between an elite tactician and an average one is enormous. It compounds over every leg of a race. Every wind shift read correctly is free distance. Miss one, and your competition sails through a pressure band you never found. Boat handling, tacking, speed, grinding, mark rounding, has a much higher floor. Every competitive sailor tacks reasonably fast. The variance is small. The leverage is in the eyes, not the hands. A standard race course runs upwind and back down. The start is managed by signal flags and horns. 5 minutes to start, flag up, horn sounds. 4 minutes, same. 1 minute, warning horn. 0, the gun. The goal: be at the favored end of the start line, at full speed, crossing within 1 second of the gun. Too early, and you return and restart while the fleet sails away. Too late, and you are already behind. The most fundamental racing rule: starboard tack has right of way over port tack. Port is left, both 4 letters. Starboard is right. Well, wind over your starboard side, you are on starboard. You have right of way. Wind over your port side, you give way. In the final seconds before the gun, boats on starboard can hold their line, cross-time their approach on starboard to own that space. One end of the start line is almost always favored. The wind angle makes it geometrically closer to the first mark. The windward mark is directly upwind. You cannot sail straight at it. You tack back and forth, hunting shifts. 2 more terms. Which tack you are on means which side the wind comes from. Starboard tack if wind is on your right, port tack if on your left. A lift is a wind shift that lets your bow point closer to the mark. Free distance. A header pushes your bow away from the mark. Lost distance. The key: a header on one tack becomes a lift if you tack. Same shift, opposite effect. Staying on the lifted tack means staying on whichever tack is pointing more toward the mark. The ley line is the angle at which you can tack once and make the mark without tacking again. Hit it too early and you sail a wide arc of extra distance. Overshoot and you give up boat lengths coming back. At the mark, inside position wins. Bow overlapping the stern of the boat ahead within 3 boat lengths. Call room. They must give you space. Wide approach in, tight exit out. Tack immediately. A header on one tack is a lift on the other. The shift just handed you free distance, but only if you take it within seconds. Every position on a racing boat has a different skill ceiling and a different skill gap between the best and the rest. The helmsman's ceiling is feel. Amateurs steer to a number. Elite helmsmen sail in the groove, the razor-thin band between pointing high and maintaining speed, for hours without drifting. Half a degree of pointing ability over a full upwind leg is hundreds of meters of free distance. The tactician's ceiling is prediction. Anyone can react to a wind shift after it happens. The elite tactician calls the shift before the fleet feels it. Highest skill variance of any role. A great tactician on a slow boat regularly beats a fast boat with a weak one. When the trimmer's ceiling is sensitivity. Amateurs set the sail and leave it. Elite trimmers adjust every 10 seconds. A constant conversation between sail shape and boat speed. The bowman's ceiling is athleticism under pressure. On a pitching foredeck in 20 knots, setting a spinnaker hoist while the bow buries, the difference between fast and smooth versus chaotic. A wrapped spinnaker loses the race. The grinder's ceiling is timing. Grinding hard at the wrong moment slows the tack. The best grinders anticipate load, pre-position, and finish exactly when the trimmer needs the last inch of sheet. The navigator works below deck with instruments, charts, current tables, and weather data, telling the tactician where the pressure is going to be in 20 minutes, not just where it is now. On offshore races, this role decides the whole race. On short course racing, it is less critical, but still the difference between sailing into a fading breeze and routing around it. On a 3-person boat, every roll stacks. The helm steers and calls tactics simultaneously. The bow crew handles the jib, runs the foredeck during spinnaker sets and drops, and calls right-of-way situations. The middle crew runs the main, manages halyards, and handles the pit. During attack, helm turns, bow releases the old jib sheet and grinds the new one. Middle manages the traveler, the sliding car on a track that controls the mainsail's angle from side to side. The whole crew rotates sides. 3 seconds on a competitive boat. Everything a large team divides between 8 people, 3 people do simultaneously. The mistakes are more costly. The physical demand per person is higher. True wind is 12 knots from the north. Your mark is due north 2 miles away. You're going to sail straight at it. Your boat's optimal VMG angle is 42 degrees. Which tack do you start on and why? How many tacks will you need? If halfway up the course the wind shifts 10 degrees to the west, what does that do to your ley line? And do you tack or hold? Between what two angles are you weaving, and what formula tells you when to stop? The polar gives you the angle. VMG equals boat speed times cosine theta. The tangent to the polar curve gives you the exact theta to target. Everything else, the shifting, the reading, the calling, no formula can precompute that. It is earned on the water. This is the physics and tactics layer. The hands-on part, rigging, docking, reading the water for the first time, comes with time on the water. But understanding why the boat does what it does makes every hour on the water faster.